Hello, Calc students. This is Mr. Allen here, and today we are going to look at section. Oops, my screen here. Go. Today we are going to look at section 8.1. We're going to start our chapter 8 material, which is on infinite series actually, but we're going to start with sequences. Section 8.1. So we would like to be able to write the terms of a sequence. We'd like to determine whether a sequence converges or what we call diverges. We want to be able to write a formula for the nth term of a sequence and use properties of monotonic sequences. A sequence is defined as a function whose domain is a set of all positive integers. Although a sequence is a function, it is common to represent sequences by using subscript notation rather than function notation. So for example, the sequence 1, 2, 3, 4, ... we would call the first term a sub 1, a sub 2 would be the second term, a sub 3. 1 is mapped onto a1, 2 is mapped onto a2, and so on. The numbers a1, a2, a3, etc. are the terms of the sequence, and the number a sub n is the nth term of the sequence. The entire sequence can be denoted by brackets a sub n. So the terms of the sequence a sub n are equal to, in this, so here's our definition. The definition for each term is 3 plus negative 1 to the nth power. So what that means is, if we did the first term, you would plug 1 in for n. So if we plug 1 in for n, and that's what we're talking about right here, that's going to be 3 plus negative 1 to the 1. So that's 3 plus negative 1, which is 2. If we plug 2 in, that's going to be 3 plus negative 1 squared, which is 3 plus 1, which is 4. And then the next term is 2 and then 4. So these are this is our sequence of terms right here. So it's just alternating between 2 and 4. Here's another example of a sequence. This sequence, we'll call it b sub n. It is given by the definition n over 1 minus 2 times n. So first thing we do is we just substitute 1 in for n. So clearly this is going to be 1, and we're plugging 1 in here. So that's going to be 1 over 1 minus 2, which is 1 over negative 1, which is negative 1. So that's where this negative 1 comes from. We could then do 2. We plug 2 in for n. We'll get negative 2/3, and then negative 3/5, and negative 4/7, and so on. So notice that this sequence is obviously very different than the first sequence. Both sequences, we are given a definition for each of the terms. Here's another example. I'll let you look at this one on your own, but this fourth example is different. The fourth example, I'm going to give the definition recursively. Recursively means that we basically are going to give you a rule for finding the next term in the sequence. And here's how it works. First of all, we typically have to give you at least the first term. So in this case, d sub 1 is equal to 25. In other words, the first term of this sequence is 25. And then this is the rule. I'll do it in purple. This gives us the rule for the n plus 1 term, or the next term in the sequence. So to find the n plus 1 term, we just take the nth term minus 5. So since our first term was 25, the next term would be 20, the next term after that would be 15, and the next term after that would be 10. So those are a couple of different ways that we could define a sequence. We could just give you the formula explicitly for each term of the sequence, or we could define it recursively. Limit of a sequence. Sequences whose terms approach a limiting value are said to converge. This is a word we're going to use a lot in the coming weeks. So for example, the sequence of 1 over 2 to the nth power. This sequence converges to 0. In other words, if we take the limit of the nth term of this sequence, if it's equal to a real number, then we say it converges. In other words, if the limit, in this case, as n goes to infinity, n goes to infinity, and here's our nth term of 1 over 2 to the n, well, that turns out to be 0. And 0 is a real number, Therefore, we would say it converges. If it does not equal a real number, we then say it diverges or doesn't exist. So here's kind of a graphical representation of what we're kind of talking about. I'm going to leave you, if you want to look at all the words up there in the epsilons. Here's the idea. So if we think that here, each of these dots represents a term of the value, the numeric value of a term of a sequence. So let's say this is the first term. This here would be a sub 1. Then here's a sub 2. And then as we go to the right, we're getting to the next. These denote the number of the term. What I want you to think of is this. So the first term was high. Then the second term was low. Then it went high, but not quite as high as the first one. Then it went low. It actually went lower than the second one. But what's happening is it's going up and down, but it's doing it and it's approaching this limiting value. Now the width of this band right here from the middle to the top, by the way, the middle number is the limit. Let's just say it's 7. That is epsilon. So the idea is this, is after so many terms, every term in the sequence will be within an epsilon of the limit L. We can talk more about this later, but that's just kind of a graphical idea of what's going on with the sequence. So for example, in this last one, all the dots are actually going to be going to 0 in this case. Here it'd be x equals 0, right? Or y equals 0. Okay, so a couple of theorems. Theorem 8.1, the limit of a sequence. Let L be a real number, and let F be a function of real variables. In other words, we're not going to deal with imaginary stuff. If the limit of f of x as x goes to infinity is equal to L, right? We've seen this before. Then what do we call that? We call that a horizontal asymptote. If you remember that all the way back from chapter 1. So this is back in chapter 1 of Calc AB. Now look at for a sequence. If a sequence, if the sequence a sub n is a sequence such that f of n is equal to a sub n for every positive integer n, then the limit of the nth term of that sequence as n goes to infinity will also be equal to L. So this is kind of connecting the ideas from what we've done with our function analysis to that of sequences. So for example, we want to find the limit of this sequence, this is the nth term, okay? And just to spell out, like, let me give you a couple of those terms. So a sub 1, you would plug 1 in here. So a sub 1 is going to be 1 plus 1 over 1 raised to the 1, so it's going to be 2. A sub 2, you would do, let me just go ahead and give you that one too, it's going to be 1 plus 1 over 2. This should seem kind of familiar. So then this is going to be, well, let's see here, that'd be 1 plus 1/2, which is 3/2 squared. So that's going to be 9/4. So that's going to be 2 1/4. And so what we can do is we can use our previous theorem right here. And what we can do is we can say, all right, we'll think of this thing here as a function f of x. And we'll take the limit as x goes to infinity. And I hope that you guys recall that that limit is e. That is actually one of the ways we can define the constant of e. So we can apply theorem 8.1 to conclude that the limit of the nth term of our sequence is going to be equal to the limit of the function as n goes to infinity, in this case e. So I'm telling you that the limit of this sequence, the nth term of that sequence, is going to be e. So again, here's a very important theorem. Okay. All right, there are different ways in which sequences can fail to have a limit. One way is for the terms of the sequence to increase or decrease without bound. In other words, they go off to infinity or negative infinity. And that's what this is saying down here. Some properties of sequences, they're very similar to properties we've learned in the past. Turns out if the limit of a sequence is L, and the limit of the sequence is K, if I multiply a constant, a scalar, times my sequence, then I can simply take C times the limit. If I'm going to add or subtract two sequences limits, well, then their sum or difference is just going to be the sum or difference of the limits. Product rule works and quotient rule works. So some very nice properties that can help you make some of the more complicated sequences, break them down into easier pieces. All right, we're going to use a symbol called factorial quite a bit in this chapter. The definition basically is this. N factorial is simply the product of 1 times 2 plus times 3 times 4 all the way up to n. So for example, 3 factorial is 1 times 2 times 3. In other words, it's 6. That's what 3 factorial is. Turns out 0 factorial, we go ahead and just define that as 1. Oh, by the way, I guess I already did 3 factorial. Factorials follow the same convention of order operation as exponents. So we just need to keep that in mind. So if I'm going to find these two things right here are okie dokie, but notice that that is different than this down here. Okay, so 2n factorial, you're basically doing the n factorial. But if I'm going to do quantity 2n factorial, that's going to be a different product simply because we're dealing with order of operations. So so let me make sure I'm saying this again. The same convention as order of operations as exponents. So it's a higher precedent than multiplication. Another useful theorem is the squeeze theorem. I am only going to mention this to save some time, but this is theorem, or not this particular theorem, but there's actually a squeeze theorem we used back in chapter 1 for limits, back in Calc AB. This has been on the AP exam. In fact, I think it was on the AP exam last year. So I would encourage you to look at the squeeze theorem. The idea is basically you've got two functions that squeeze together and allow us to prove that a limit exists. We can do the same thing here with sequences. We try to bound it above and bound it below to show that the limit exists. The absolute value theorem, please put a star next to this one. This one is very important. Here's what the absolute value theorem says. It says for a sequence a sub n, if the absolute value of the nth term of the sequence as n goes to infinity is 0, then the limit of a sub n without the absolute value symbol as n goes to infinity also has to be 0. This is not intuitive, but is very helpful. You will use it on some problems. Sometimes the terms of the sequence are generated by some rules that do not explicitly identify the nth term. So the example I did earlier, we did do that. I gave you the explicit definition. In such case, it may be required for you to discover the pattern. This is the part where it gets interesting. You're going to have to try to come up with the nth term. Once the nth term has been specified, you can investigate if it converges or diverges. So here's an example. So here are some terms of a sequence. Now notice I've not given you the nth term formula. You don't have the formula. You just know what, here's a sub 1. A sub 1 is 2. A sub 2 is 4 over 3. A sub 3 is 8 over 5. And you're supposed to determine whether a particular sequence converges or diverges. So the first thing you got to do is figure out what the nth term is. So let's go ahead and look at that. So first of all, we'll notice from this previous slide, all of these powers in the numerator are powers of 2, and everything in the bottom is an odd integer. So in other words, basically what we're going to do is we're going to use this. This is going to be our rule. So it turns out, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. So that's, you can see where the numerator is coming from. Now the bottom, the rule for odd integers is just 2n minus 1. So if n is 1, 2n minus 1 is 1. If n is 2, 2 times 2 is 4, minus 1 is 3. So this is the nth term. So a sub n is as follows. Let me go and put that on this last slide. So a sub n is 2 to the n over 2n minus 1. Now, let's go ahead and use theorem 8.1 and see what we can find when we take the limit of the function that is basically equivalent to that nth term to infinity. Now, it turns out if you do a direct substitution here, you're going to get infinity over infinity, which is an indeterminate form. So what we would do then is use L'Hopital, and that's what's happened here is we've applied L'Hopital's rule, and we can see, and this is, I should probably write that in here, L'Hopital. If I can spell L'Hopital, that's an H, sorry, L'Hopital. So now we can apply theorem 8.1 to conclude that notice here, we've shown that the function goes to infinity, but then we can use 8.1 to say that the sequence, the nth term goes to infinity. So therefore, this sequence diverges. So let me go through that process again. So what we did is we were given this sequence right here. Let me clear off all of that stuff. We were given a sequence. And then what we did is we found the nth term of that sequence. This one worked out pretty nicely because we have powers of 2 on the top and just odd integers on the denominator. We went ahead and used our, we just created a function that's equivalent to the nth term of that sequence, took x to infinity. We saw that was infinity. Then we utilized theorem 8.1 to show that this has to diverge. Okay, monotonic sequence, that just means it's either constantly increasing or constantly decreasing. So we say monotonic are non-decreasing. So what's that mean? That means the terms are getting bigger. And we say that it is non-increasing, that means that the terms are getting smaller. So this fourth example here, we're just trying to determine if a sequence is monotonic. So let's just go and look at these one at a time. So here's sequence A. Sequence A is 3 plus -1 to the n, which I've already kind of sketched a graph. And we already saw this one earlier. This is the one that alternated between 2 and 4. Well, this is clearly not monotonic. And the reason it's not monotonic is because in order for it to be monotonic increasing or decreasing, it would have to either constantly be getting smaller and smaller or constantly be getting bigger and bigger. And that's clearly not the case. It's alternating between two values, so it's not monotonic. Let's look at B. B was this sequence right here, 2n over 1 plus n. Now what I've done is I've just drawn the first 4 terms here. We can clearly see that as we go to the right, that this is increasing. And note that because n is positive, you can simply multiply the size of the inequality of 1 plus n and 2 plus n without reversing the inequality. So this is, we can clearly see that this is going to be monotonic. And so what we're doing here is we're multiplying the numerator by 1 plus n, and then we get the following. We substituted n plus 1, and that gives us b sub n plus 1. And then what we can do is basically just do some rules of algebra here to simplify this. So we can just go ahead and cross multiply here. Once we cross multiply here, we can go ahead and FOIL things out. And then we can subtract the things that are on both sides. So for example, I can cancel this and this, and then I can cancel that and that. So we're left with 0 is less than 2. 0 is always less than 2. So starting with the final inequality, which is valid, you can reverse the steps to conclude the original equation is also valid. So therefore it's monotonic. Finally, if we look at this one, and you can just look at the graph here, and you can tell it goes up, but then it comes down. So this one is not going to be monotonic. This is not monotonic. Let's go ahead and finally talk a little bit about monotonic and bounded sequences. So bounded above just means that as your sequence is growing, it grows, but it never gets above some finite value. Similarly, if it's below. We say though, and this is part maybe you should maybe know, we say it's bounded if it's bounded above and below. So we can say specifically it's bounded above, and we can say specifically it's bounded below. We just say it's bounded if it's both bounded above and below. So let me just kind of get to cut to the chase here. Here's our last theorem, and it's theorem 8.5, and it's the bounded monotonic theorem. This is very powerful, and it's used a lot in analysis. If a sequence is bounded, that means it's bounded above and below, and it's monotonic, which means it's either constantly growing or constantly decreasing, then it has to converge. It has to converge. Here's an example. I'm going to kind of go through this quickly. So we're going to look at the sequence 1 over n, which is both bounded and monotonic. So why is it bounded? Why is it bounded? Well, if we think about 1 over 1, that's the first term, and then 1 over 2, that's the second term, and then 1 over 3, that's the third term, etc. Clearly, it doesn't get any higher than 1. And if we think about, if we don't let n go to infinity, at infinity, it goes to 0, but it never quite reaches 0, right? So it's bounded above and below, and each of the terms is getting smaller and smaller. So this is bounded and decreasing. So this is bounded and monotonic. Oops, I guess I should erase that. And then here's a couple more. This one here is monotonic, but it is not bounded. It actually grows without bound. It goes to infinity. It's bounded below. And then this one here is not monotonic because it just alternates between 1 and -1. And that is a